Now, the whole problem with series is that, well, there's a lot of them. And they don't all have nice formulas to tell us whether or not they converge or not. So even something like, say, the series taking the sum of 1 divided by n times n plus 1, well, that almost looks like the harmonic series, but the denominator is different. Maybe I could calculate some partial summations and see if there's a pattern. This one kind of looks like that telescoping sum problem that I did from last week, so there might be some cleverness there. But I can't really bank on being clever every single time. It's great, it's fun, but not always the most reliable solution. So if I had a series that I want to test, the test should come back and say, yes, the series converges, or no, the series diverges. Maybe my test is not able to give me an exact value for that summation, but at least tells me that there should or should not be a number at the end of that process. So I want to turn this series into an integral, which I'm going to compute instead. So let's look at a fairly simple series. The terms of this series are 1 divided by n. So we start off at 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over 25 and so on. Again, this isn't quite the geometric series and it's not quite the harmonic series, so neither of those examples from last week will help us here. So you might start off by trying to compute some partial sums, or at least getting a computer to calculate partial sums for you. And if you did that, you'd get a table that looks kind of like this. So the fifth partial sum of this series is 1.46 and change. The 10th partial sum is 1.54 and change. The 50th partial sum is 1.62 and so on. The 5,000th partial sum, so taking 5,000 of these numbers in a row, adding them all up, we get 1.6447. So this is a very, let's say, old school way of handling a limit where we're just going to calculate those numbers and see if they get close to anything. So that's kind of about as bare bones as you can get. But I want to use a tool to figure out whether or not this limit is convergent or not. So let's look at all of those numbers, right? The first number is 1 on 1 squared, the second number is 1 on 2 squared, the third number is 1 on 3 squared, and so on. And let's think about them as representing areas. So for each value of n, for each positive whole number, I'm going to draw a rectangle. And each of my rectangles is going to have width 1 and height equal to whatever that number in the list is. So my first rectangle has height 1. My second rectangle has height 1/4. My third rectangle has height 1/9. My fourth rectangle has height 1/16, so on. And I'm going to line them all up next to each other along the x-axis, right? So far, just a geometrical exercise, just a nice picture to help think about things. But one thing to notice here is that when I draw my boxes this way, the upper right-hand corner of every single rectangle is going to fall along a curve, a particular curve, right? So this coordinate right here is 1, 1. This coordinate here is 2, comma, 1/4. This coordinate here is 3, comma, 1/9, and so on. So each of the upper right-hand corners of the rectangles is going to be on the curve y equals 1 divided by x squared. Well, I think I could do some calculus with that.